Hello students, I wanted to do a quick example of a combustion analysis problem. Combustion analysis is a technique that we use in order to find the empirical formula or percent composition of a compound when we don't know what the compound is. So a classic thing that we do here is when we have something like a hydrocarbon and we want to know how much carbon and how much hydrogen are contained within that compound. So I'm going to do an example with a simple hydrocarbon. That is when it just has carbon and hydrogen in it. And my example says that I have 1.5 grams of my hydrocarbon. And when it undergoes complete combustion, I get 4.4 grams of CO2 and 2.7 grams of H2O. And I want to know what's the empirical formula of the compound. So first things first, I know that this one contains only carbon and hydrogen. I've added oxygen, an excess amount of oxygen, to do the combustion analysis so that my stuff that I care about is the limiting reactant, and I know that I'm going to use it completely up. That allows me to know that all of the carbon in this CO2 came from the carbon in my compound, and all of the hydrogen in my water came from the hydrogen in my compound. The oxygen, of course, I added when I was burning it. So what am I going to do? I'm going to turn my carbon dioxide, grams of carbon dioxide, into moles of carbon. Now, sometimes when you see a combustion analysis, they'll turn it into grams of carbon. That's necessary when you have something else in the compound, like oxygen or nitrogen, and you're going to have to subtract from the grams that you had initially. But we don't have to go that far because we know that we only had carbon and hydrogen, so we don't need to get to mass here. So I'll start with my 4.4 grams of CO2. I'm going to use the molar mass to turn it into moles of CO2. And I know for 1 mole of CO2, I have 1 mole of carbon, just because of the subscript. And so in the end, I'm going to get 0.09998 moles of carbon. I also have my hydrogen, 2.7 grams of water. I'll divide by the molar mass. And for water, because it has that subscript of 2, 1 mole of water contains 2 moles of hydrogen. So that gives me 0.2998 moles of hydrogen. Now that I have the moles, it's pretty easy to get to the empirical formula because what I need to do is find the ratio. So if I divide both of these by 0.09998, that gives me 1 for carbon. And for hydrogen, it'll give me 3. So I know that my empirical formula will be CH3. Now, let's do another example that's a little bit more complicated. This time we're going to have something that contains hydrogen, carbon, and also oxygen. So for this one, they tell me that I have 0.25 grams of my compound that contains carbon, hydrogen, and oxygen. And when I completely combust it, I'm going to get 0.3664 grams of CO2 and 0.1500 grams of H2O. So here I'm going to start by doing the same thing, but because I know my compound contains oxygen, and I'm also adding oxygen in order to burn this, the only way to find out how much oxygen I get is by subtracting out from my initial mass the amount of carbon that I have in my CO2 and the amount of hydrogen that I have in my water, and then whatever's left over from that initial mass, that's how much oxygen I'm going to have. So I'll start with my CO2, 0.3664 grams of CO2. I'll divide by the molar mass. I'm going to turn it into moles of just carbon. And for each mole of carbon, I know that that's 12.011 grams of carbon. And so I get 0.1000 grams of carbon. I'm going to do the same thing with my water, 0.1500 grams of H2O. Turn that into moles. Use my stoichiometry here. For 1 mole of water, I get 2 moles of H. And for 1 mole of H, it's 1.0079 grams of hydrogen. And in the end, I get 0.01678 grams of hydrogen. Okay, so now I know that I started with 0.25 grams. That was my initial mass. I'm going to subtract out 0.1 grams of carbon and 0.01678 grams of hydrogen, and that'll give me the mass that's left over, 0.1332 grams, and that has to be my oxygen, the leftover mass from my 0.25 grams that I started with. So now I know the grams of carbon, hydrogen, and oxygen, so I can set up my table to do my conversion. I know the mass here is 0.1000 grams of carbon, 0.01678 grams of hydrogen, and 0.1332 grams of oxygen. If I divide by the molar mass to get moles, this gives me 0.008325 moles of carbon, 0.01665 moles of hydrogen, and 0.008327 moles of oxygen. I've done mass to moles. Now I need to divide by small in order to get the ratio. The smallest number I've got is this one here. So I divide all three by that, and I'm going to get 1, 2, and 1 for my ratio. So my empirical formula will be CH2O. Okay, that's our example for combustion analysis. I hope that's helpful, and I hope you have a great day.